So now we have the glitching. Glitching in static CMOS network. Glitching have a non-zero propagation delay resulting in spurious transition or glitches. And this is known as a dynamic hazard. Okay, so what happens? So if you can see here, glitch occurs sometimes when there is a clock, right? And you put this clock into different gates, right? So let's say you are AND or NANDing these signals. As you can see here, when you put this multiply by this, you will get this glitch. This signal is supposed to actually end here, right? So that when you have this, if the 0 times 1, it should be a 0. But because this signal is slow, it's supposed to end, but it's still on, then it is 1 times 1, then you produce a high. You do not want this high. So this is known as a timing violation or a glitch. Okay, so how do we eliminate this glitch, or how do you control that this T1 should arrive when it's supposed to? Or if not, you have to make T2 slower. T2 doesn't arrive here. If you know this guy is going to arrive late, you have to make this later. What do we do? Okay, so we do balance delay path to reduce glitching. This will actually occur a lot when you draw the layout, right? When you do the schematic, it is not a problem because everything is ideal, there will be no delay. But when you draw your inverter, let us just draw some inverter. Okay. I wanted to change. So let's just say you have an inverter here. Color red. Right, you have your inverter. This is your input. By the end of this course, when you look at this, you already know that it's an inverter. Okay, you should be able to do that. I hope that the knowledge has been passed, that you understand that this is an inverter. I don't like my mouse. Where is my mouse now? Okay, ground, and this is output. Okay, this is the compact layout, right? But if you do not do this compact layout and your inverter is like this, sabar je lah ni mouse. Mana dia? Okay, like this. Okay, and instead of having a straight line here, let's put an eraser. Let's say you draw like this. So this is the out. Okay, and because of this wire delay, it will create a capacitance, so the output will be slow, right? And this will create mismatch. And this is the polysilicon, a long polysilicon. So this will also will produce a delay, right? Polysilicon has very high resistance, and the signal will become When it has high resistance, the signal from nice like this will become muted like this. Okay, because there is a high resistance. Okay, so as you can see here, if you have these kinds of gate, it will make the signal slower. And instead of arriving on time, it will arrive late and then very weak. Okay, so in order to, what we need to do is we have to put in a buffer or to optimize this circuit. Okay, so glitching is due to mismatch in the path length. As you can see here, this one, it arrives at F0 because the wire here is short. So it will arrive at time, let's say, t equals to 0.1. This one, because it is very far, this guy has to run, this signal has to run very far, it will be slow. It will arrive at t equals to 0.2, for example. And this third guy, this poor guy, will arrive even later, t 0.3. Because of this, these signals will not turn on at the same time. And then, for example, this is the AND gate, A, B, C, D. So C and D will arrive late, and this will create glitch. In order to do that, you can balance them so that this one, everybody arrives at the same time at t equals to 0.1. All right. So you can put it that way so that all the inputs of the signal arrive at the same time and no glitching occurs. Okay. Power and energy design space. All right. So this is what we did just now. We have done. We haven't done that. We have, okay. For dynamic, you can reduce the VDD. You can reduce the transistor size. Okay, we haven't done multiple VDD and we haven't done clock gating. And for leakage, right, we will do this later. We have multiple thresholds, stack effect, pin ordering. So these are all the techniques that can be used to reduce power. Okay, next what we are going to do is multiple VDD. Okay, so as you can see here, dynamic power is a function of VDD, and decreasing the VDD decreases the dynamic energy consumption quadratically because it is a function of VDD squared. If you reduce, you will reduce the energy consumption quadratically.